Hello everybody and welcome to our webinar. My name is Vladimir Podnos. I am Director of Marketing and Support of Terra Analysis, and today with our support engineer Alex Любимцев we will discuss simulation of the electric current flow analysis problems with QuickField. For those who are new to QuickField, let me briefly outline what is QuickField. Our product is a finite element simulation system, mostly 2D, for a wide range of electromagnetic heat transfer and structure analysis problems. Mostly because we currently have 3D extrusion electrostatics and about to release a new version which allow three-dimensional CAD step files import from major CAD systems for electrostatic analysis. But all other components of QuickField are for planar and axial setups only. So the full range of analysis types includes magnetic analysis suite with DC, AC, and transient magnetic packages, electric analysis suite, which includes electrostatics, AC and DC conduction, and nonlinear transient electric analysis packages, and thermostructural suite, which includes static and transient heat transfer and static stress analysis packages. Subset of electric analysis suite, DC and AC conduction and transient electric analysis packages may be applied for tasks related to electric current flow analysis. Specific engineering tasks which are related to such kind of problems may be very wide. They may arise in ground connector or heated car windows design. They may be required for analyzing surge currents and contact resistances in electric equipment, or electrode design, and many other practical applications. My colleague Alex will demonstrate how to apply QuickField to some of them. QuickField is a multi-physical tool. Means we support various types of analysis for the same geometry, and we allow transferring results of one simulation to other simulation. And this is very important because in many cases the current flow analysis requires taking into account both electromagnetic processes which generate the heat and then calculation of the temperature deformations or other combination of electromagnetic heat transfer and stress analysis in one task. Other feature of QuickField, its open object interface, which allow combining QuickField core with external models written in MATLAB, C++, Visual Basic, or using other major programming platforms, allows easy extension of the set of features of QuickField core or adapting of QuickField core to specific needs. And major advantage of QuickField, which makes it really unique, is ultimate simplicity. QuickField requires no training. I hope you will agree with this statement after seeing the live presentations of QuickField simulations shown by Alex.
In our practical part, the 7 tasks will be reviewed. The first task is the conducting plate resistance calculation. Then we will analyze the ideal contact between two plates and will calculate the contact resistance in case of non-ideal contact. We will also simulate the ground connector. Then we will simulate the film heater, the thin film carrying electric current, and this film is used as the heater. And we will simulate AC conduction problem and calculate the leakage current in a three-phase cable, and we will simulate the transient electric problem and calculate the surge current in the resistor. Now we start with the first case. This is the conducting plate made of steel Two electrodes are connected to the plate, and our task is to calculate the resistance of the plate. We know the electrical conductivity of the material, and we know the dimensions of the electrodes and the plate. The plate thickness is 1 millimeter. The total length is 26 millimeters and the height is 6 millimeters. This is a simple problem, so I will start QuickField and will do the simulations from the very beginning. So this is QuickField, and I will create the new problem. I choose the folder where the problem will be created and specify the problem name. Next, I should specify the problem type. I have the DC voltage applied to the plate, so I choose the DC conduction problem type. Also, I specify the length units, and the thickness of the plate is 1 millimeter. Now this is the geometry editor window, and here I should draw the plate. The plate has a length of 26 millimeters. You can see the coordinates here in the right bottom of the screen. And the height is 6 millimeters. Here is the one contact plate, and here is the another contact plate. The geometry model is ready. Now we should assign the labels to geometric objects. This would be the plate. This is the electrode, the positive electrode, and this is the negative electrode. Now I have the geometry model ready, and I have the objects labeled. Next, I should assign the material properties and boundary conditions to these objects. For the plate, I specify the electrical conductivity of the steel. For the negative electrode, I specify the voltage. For the positive electrode, I specify the voltage. And the last step before we start the solving is to build the finite element mesh. Just press the button and the mesh is ready. Now we can save all the problem files and run the simulation. Here you can see the color map of the current density distribution in the plate. I will adjust the field picture and switch on the color map of electric potential and the vectors of the current density. Now you can see how the electric current flow in the plate. To measure the resistance of the plate, I need to know the voltage drop and the current. The voltage drop I already knew. It is 0.02 volts. So I should measure the current. I will use the contour tool and build the contour across the current paths. Now I can calculate the integral value current through the surface. This is the current crossing this integration surface. And the resistance now is voltage drop divided by the current. .3 milliohms. This is the resistance of this steel plate. QuickField allows you to change the geometry rapidly and adjust many parameters. For example, I can change the electrode length from 6 to 10 millimeters. Solve the problem again. And this is the result. I will adjust the field picture and measure the current. You see, it was 53 amperes and now it's 65, so the resistance now is lower because I changed the electrode size. Now let's move to the more complicated case. This is the ideal contact between two plates. There are two bus bars, the copper and the steel bus bar. And our task is to design the contact plates between these bars. Here it is specified that the contact area has the length of 15 millimeters. Perhaps we should increase or we may decrease this length. Again, this is the simple case. I will use QuickField and simulate the problem from the beginning. I create the new problem. Specify the problem name and the location folder. Here I choose the problem type. The constant current is flowing in my conductor, so the problem type will be DC conduction. The length units are millimeters and the bus's width is 50 millimeters. Now I can draw the geometry model. The copper bus has the height of 5 millimeters and the steel bus has the height of 10 millimeters. So this is the steel bar. And this is the copper bar, and our task is to design this contact. So let's move this plate in contact. Now here they are in contact. There is no need to draw something specific. If two blocks are connected through the edge, the current will flow. So now I have the small contact area of 1 millimeter of length. Now let's assign the labels to geometric objects. This is the copper. This is the steel. I set the electric potential here to be 0. And here I specify the current. Right now it's only the label. No current value is yet specified. So two bus bars, copper and the steel, the contact where the current flow and the 0 volt side. Now we should assign the physical properties. For the copper I specify the electric conductivity of copper. For the steel I specify the electric conductivity of the steel. Left side of the copper bus bar is ground connected, I specify 0 voltage. And here I should specify the current density. The total current flowing in my system is 1000 amperes. And the cross-section area of the steel bus bar is 50 by 10, 500 millimeters square. So the current density will be 100 amperes divided by the 50 by the 10, 2 amperes per millimeter square. Two amperes. Here the units are meters square, so 2 10 to the power of 6 amperes per meter square. Now I can build the mesh, save all problem files and run the simulation. Let's take a look closer at the contact place. I will switch on the electric potential color map and the vectors of the current density. You see indeed the current flowing from the steel bus bar to the copper bus bar. From here, from the right to the left, and we can measure the voltage drop. We know the current value, it's 1000 amperes, and we can measure the electric potential of this side. It's 0.056. So the resistance of this contact is voltage divided by the current. 657 microohms. Now what will happen if I move this side further to the left? The contact area will increase, so I may expect the lower resistance. Let's simulate this case. Again, I will switch on the color map of the electric potential. 55.5, and it was 56.7. So indeed, if I increase the contact area, the contact resistance will be lower. Now the question is, for how long should I make the contact resistance area? Where should I move here, or maybe even further? I don't know yet. Because if I increase the contact area at the same time, I increase the length of the steel bus bar, and the resistance for the current will increase. It is an interesting task to run the series analysis and calculate the resistance for different contact area positions. QuickField has a tool to automate these calculations. It's called the label mover. Label mover may automate this calculation. It operates with the labeled objects. So if I want to move this left side of the steel bus bar, I have to label it. So the label mover may operate it. So I assign the label left. There is no physical meanings, special physical meanings for this label. It's just the labeled for the age, so that label mover can operate it. And I do not assign any physical properties here. Now let's start the label mover. I choose the serial analysis mode in label mover. Next, I should choose the base problem. Here it is, the bus bars. Then I should specify the values to measure. I will measure the electric potential of the right side of the steel bar, where the current flows inside. So I choose the right side where the current flows and specify the average surface potential. I will measure this side electric potential. Next, I should specify the steps. I would like to move this edge to the left. So I press record steps, specify the edge to move, and will move it to the left by 1 millimeter. QuickField problem was created where this edge is moved to the left by 1 millimeter. And I would like to repeat these steps, say 20 times. Now I have the base problem, I have the values to measure, electric potential, and I have the steps to perform. Now I can get the results. You can see the series of geometric models, the series of QuickField problems are generated. Each problem is then simulated, and the electric potential of this right side of the steel bus bar is calculated and copied in the table. Now the results are ready. Here's the electric potential, and if I divide this value by the current value, I will get the resistance. Let's take a look. The current value is 1000 amperes. Let's take a look at the plot. You can see that initially the resistance changed drastically, but after 10 steps the resistance changed not so much. And each step present the shift of this side to the left by 1 millimeter. So I believe this is the optimal distance, the optimal area for the contact, about 10 or 50 millimeters. There is no need to get the great contact area, but we should avoid the smaller contact area. So I believe the 15 millimeters is a good choice for the contact area size. Now this was the ideal contact between two plates. But what will happen if we have the resistance layer here? Let's simulate this case and calculate the contact resistance. I will choose this base problem. This is the ideal contact. But now we have the thin layer. Here you can see it. This is the copper, this is the steel, and this is the resistance layer. It's a very thin layer. Its thickness is only 1/100th of the millimeter. It's 1,000 times smaller than the thickness of the steel bus bar. But at the same time, the resistance, the electric conductivity of this layer is 1,000 times smaller than the electric conductivity of the steel. Now let's simulate this case and take a look what happened in this contact area. But first I should specify the electric conductivity of the resistance layer. Now, next I should build the finite element mesh. Please note that simulation of the thin layer requires a very fine finite element mesh in this area. So the total size of the finite element mesh now is 100,000 elements. Now let's run the simulations and take a look how much time it requires. It is done. Again, I will adjust the field picture. I will switch on the electric current density vectors and the color map of the electric potential. So this is how the current flows in the resistance layer. And again, our task is to calculate the resistance of this contact. I know the current value. It's 1000 ampere. And to calculate the resistance, I should measure the electric potential difference. This side has 0 electric potential, and this side has the electric potential of 0.0556. So if I divide the voltage difference by the current, I get the electric resistance. Let's compare this value with the ideal contact resistance. You see, this is the case 20, and in case 20 we had the voltage difference of 0.054, and now it's 55 and 6. Indeed, the resistance layer increased the resistance of the electric contact. Now let's move to the next case. This is the ground connector. Ground connector is used for protection of the if the electric potential, the dangerous conducting parts, these parts are connected for the ground connector, and the electric current flows to the ground. Important to have the low resistance of the ground connector, so the voltage drop between the zero potential at the ground and the protected devices not be very large. Our ground connector consists of 3 steel rods placed in the ground 1 meter beneath the ground surface. The distance between rods is 2 meters. This ground connector is designed with a voltage rate of 220 volts. The rod diameter is 4 centimeters and the axial length of the rods is 4 meters. The soil electric conductivity is 0.1 Siemens per meter. Our task is to calculate the resistance of this ground connector and compare the value with the required resistance value of 4 ohms. Again, this is this very simple geometry model, so I will start QuickField and simulate it from the beginning. I create the new problem, specify the problem name and the location folder. The problem type again is DC conduction, and the model class is plane parallel, and the length units are meters. Now here I will draw the single electrode. The single rod, it has the diameter of 4 centimeters. This electrode is placed beneath the Earth's surface, so I will move it by 1 meter down. And there are 2 other electrodes placed one from each other. The distance between the electrodes is 2 meters. So these are the electrodes. Now I should draw the ground surface. I will use the small piece of ground about 100 meter in width and about 50 meters in depth. So this is the geometry model. And again, here I should assign labels to geometric objects. This is the soil. And these are the rods. And far away, about 50 meters from the rods, I believe the electric potential would be 0. Now I should assign the physical properties for each object. For the soil, I specify the electric conductivity of the soil. It is 0.1 siemens per meter. For the rods, I specify the electric potential of the device. It's 220. I will specify the peak value. So it's 220 multiplied by the square root of 2. This is the peak value of the voltage. And far away from the rods from the ground connector, the potential drops to 0. So here I specify 0 voltage. Now we can build the mesh and run the simulation. You can see the field lines are not, the field distribution looks strange and the field lines are not smooth lines. That's because the mesh quality here is not enough. We can automatically adjust the mesh. Here you should specify how many iterations you require to adjust the mesh and the mesh limit. We set 0, so there will be no mesh limit. You may note that QuickField adjusted the mesh and rebuilt it. Now let's take a look at the result. That's much better. And I will switch on the vectors of the electric current and the color map of the electric potential. I will adjust the scale. These are the electric current flowing from the ground connector in the ground. My task is to measure the electric current and to find the resistance of the ground connector. To measure the current, I simply build the integration contour that crosses the current path and calculate the current through the surface. I know the electric potential, the voltage, the rated voltage of my device, and I know the current, so I simply divide this is the mean square. I should multiply it to get the peak value by the square root of 2 and divide this peak voltage value by the current value, 25.6. Now you can see that the resistance of the ground connector is 12 ohms. Please note that this is the plain parallel problem and all the values are calculated per 1 meter of problem depth in the direction. So I can open the problem properties and choose the problem length to be 4 meters. There is no need to calculate the current in case of the rods with the length of 4 meters will be 102 amperes. Again, if I divide the voltage, the peak voltage by the peak current, the peak value of the current, I get the 3 ohms. So the ground connector with the length of the rods of 4 meters features the grounding resistance of 3 ohms, which is lower than the required grounding resistance 4 ohms. So it's used for our purposes. Next, we will review the heating effects of the flowing electric current. Sorry, one step back to the ground connector. The important parameter of the ground connector is the step voltage. So I will remove the integration contour and build the contour along the Earth's surface. And I will like to measure the electric potential distribution along this surface. So I build the contour and switch to the XY plot. Now this is the electric potential distribution on the ground surface in the area of the ground connector and 50 meters to all sides. And you may note that if we take the steps of 1 meter, the voltage drop here is about 5 volts. Next step, the voltage drop 5 volts. Next step, the voltage drop is 25 volts. So this is the dangerous area where there is the high step voltage drop. Next step, it's about 22 volts. Again about 20, and the next step is only 10 volts. So the most dangerous area is not the very top, the very place where the ground is connected, but 3-4 meters to the side of the ground connector. This is the most dangerous area. 4 meters away from the ground connector. Now let's move to the next example. And this is the thin conducting plate used as the electric heater. You know, the electric current flowing in the conductor causes the electric losses, and the losses cause the heating of the conductor. So our task here is to calculate the temperature distribution in this plate. This is the steel plate, the steel foil, we know the electric conductivity of the material. We know the thermal conductivity. We know the convection coefficient from this plate is cooled by the air flowing around. And the ambient air temperature is 0 degrees Celsius. Our task is to calculate the resistance, the current distribution, and the temperature of this film heater. Let's start with the electric part. This is the geometry model, and this is the DC conduction problem. The plate, the film width is 1 millimeter. The electric conductivity is 10 megasiemens per meter. And on the left side, it has the electric potential of -100 volts. And on the right side, we have the electric potential of plus 100 volts. And our task, the first part of our task, is to calculate the current distribution. This problem is already simulated, so I will just open the field picture. I will adjust the field picture again and switch on the current density vectors and the color map of the electric potential. Here you can see how the current flows in the plate. We know the current density. We know the electric conductivity. We can calculate the losses. Again, I will adjust the field picture and switch on the Joule heat color map. You see, the higher the current density, the higher the losses. The next part of our task is to calculate the temperature distribution. In fact, this is the three-dimensional problem. The plate is cooled from all sides. But we know the trick. You can substitute the convection from the front side and from the back side with the negative heat source. You may note that the equation that described the convection heat flux, this is the convection coefficient, this is the temperature difference, and this is the surface area. This is the convection from the front and the back side together, the convection heat flux. And this is the heat sink, which could be not only the constant value, but could be also the function of the temperature. The volume heat sink. We can adjust the coefficient so that the volume heat sink will take this same as the natural convection. So let me show you how this trick is done. Back to QuickField. So I need to calculate the temperature and transfer the losses from the electric problem to the transient problem. You can see the losses are not uniformly distributed in the plate. And the best way to transfer the losses is to create the coupled problem, where the one problem is linked to the another problem. So I create here the new problem, the thermal part. This would be the steady state heat transfer problem. This thermal part will use this same geometry model as the DC conduction part. And of course it should have the same model class and the thickness. Now this is the steady state heat transfer problem based on the same geometry model as my DC conduction problem. Steady state DC conduction, and they share the same geometry model file. In heat transfer problem, I should specify thermal properties. I have the convection on all sides of the plate. The convection coefficient is 10 and the ambient temperature is 0. These two sides are connected to electric circuit, so there are no convection from the left and from the right side. And for the bar, I should specify the thermal conductivity, which is 380, and to specify the convection from the front side and from the back side, I will use the negative volume power source. This power source will depend on the temperature. And all I need to know is this coefficient that can be calculated using the convection coefficient and the thickness of the plate. So for 0 temperature there will be no heat flux, and for the 100 ampere I specify the heat source. You can see now I have the volume power heat source as a function of temperature. And using this trick, I will simulate the convection from the front and from the back side. Now I have the geometry modulator and materials properties ready, and next I should import the power losses from electric problem to the thermal problem. So I open the thermal problem properties and follow to the links tab. Here I choose the data link type, the generated heat, and select the problem that contains this type of data. I add the link. Now it's present in the tree. You see that the thermal problem is now linked to the electric problem, and the general heat is transferred from the electric problem to the thermal problem. And now I can run this simulation. Here you can see the temperature distribution in this film heater. Where the current was great, the temperature is great too. But it's good conductor, so the temperature difference is not so drastic as the difference in the current density and the joule heat value. You may note that the plate was heated by about 4 degrees. And you know that the electric conductivity depends on the temperature, so we can iterate through these two problems. We can open the electric conductivity problem, specify the temperature here, specify that the electric conductivity is function of temperature. For 0 temperature it's 10 megasiemens, and for high temperature the conductivity will be lower. The higher the temperature, the lower the conductivity. We can run the simulation again. get the new value of the Joule heat distribution, and run the thermal problem again and get the new temperature. And we can repeat this iteration several times to get the actual temperature and the actual Joule heat produced in the film heater at this temperature. And we move to the next case. The previous cases was dedicated to the direct current, and this case is the AC current in the dielectric media. This is the three-phase electric cable. There are Joule heat losses in the conductors because of the current flowing in these conductors, but even if there are no current, there is the leakage current. If there is no current in conductors, there is the leakage current between conductors, because each phase has its own electric potential. We know the electric frequency, we know the insulation electric conductivity, which is very low value, and we know the insulation electric permittivity. Our task is to calculate the power loss in dielectric media caused by the leakage current. The cable voltage is 220 volts RMS value. Now let's start QuickField and I will show you this case. This is the AC conduction problem, and for the AC conduction problem I should specify the frequency of the current and voltage. This is the plain parallel problem, and all the losses, all the currents are calculated per 1 meter of the model depth in Z direction. In the geometry model I have the insulation between conductors, and for the insulation the electric permittivity and the electric conductivity are specified. And I have the cover of the cable. Again, electric permittivity and conductivity are specified for the cover material. And I have three-phase conductors, A, B, C. For each conductor I specify the voltage. This is the peak value of the voltage. So you can see it's multiplied by the square root of 2, and I specify the phase in degrees. For the phase B, the phase is 120, and for the phase R, the phase shift is 0 degrees. The cable is buried in the ground, so this is the cable surface and it has the zero potential. And there is the null conductor in the cable with zero potential. Now we have two conductors with the same value, with the same amplitude, but with the different electric phase of the electric potential, and there will be some leakage current between conductors, and there will be leakage current between the conductor and the ground. Now let's take a look at the simulation result. This is the electric field strength distribution. I will adjust the field picture and switch to the electric potential distribution, momentary values, and the current density vector plot. As it is the alternating current, the picture will change in time. So I can switch on the animation and see how the electric potential distribution changes and how the electric current, the leakage electric current in the insulation changes in time. But my task is to calculate the losses. There is electric current in the insulation. I know the electric conductivity insulation. I can calculate the losses. I select the insulation media and calculate the active power produced in the volume integral. So the average value of the losses is about 0.25 watts per 1 meter of the cable length. The last case for today is the transient electric current, which flows in the lightning arrestor. Lightning arrestor is used to protect the devices from the lightning or the voltage. The lightning protector device consists of the insulation tube, high voltage part, and the grounded part. And inside there is the special material, the zirconium oxide. And this material features the high electric permittivity and nonlinear electric conductivity, which depends on the electric field strength. And our task is to calculate the current flowing in this nonlinear media when the high voltage impulse of the lightning is arrived. So I start QuickField. You can see now this is the transient electric problem, as the pulse is not a constant function, it changes in time. It's not a sinusoidal function, and I have to perform the transient analysis. The model class is axisymmetric. This means that the model features the rotational symmetry, where the x is the horizontal axis of rotation, and I should draw only the upper half of the cross section of my device. And as this is the transient problem, I should specify the timing. The integration, I should specify the integration time step and the final calculation time. Now, what have what do I have in my model? I have the air which is surrounding my arrestor. For the air, I specify the electric permittivity of 1. I have the ceramic tube. And for the ceramic tube, I specify the electric permittivity of ceramic and the electric conductivity of ceramic. And inside this tube, there is the zirconium oxide that features high relative electric permittivity and nonlinear electric conductivity. The higher the electric voltage potential, the higher the electric stress. In the media, the higher the electric conductivity. The right side is ground connected. It has 0 electric voltage. And the high voltage side has the constant electric potential value of, and then the surge, the lightning pulse rise. You can see this is the function of time that describes this lightning voltage pulse in time. For transient problem, QuickField understands not only the constant value but also the functions. Now let's take a look at the simulation result. Here are the electric potential lines, and as we simulate the transient problem, we can take a look at the field distribution at different moments of time. I will adjust the field picture and switch on the color map of the electric field trend. Now let's take a look at the initial moment of time where the electric potential has the nominal value of 35 kilovolts. You see the electric field stress in the media has very low value. But as the voltage rises, as the lightning pulse arrives, the voltage rises and the electric field stress rises as well. And at some moment of time, the electric stress is so high that the conductivity of the zirconium oxide increases and the active current flows. Now let's measure the electric current. We can switch on the vectors and see how the electric current flows. We can switch on the animation and we can measure the current value. I draw the contour, the integration contour crossing the current path, and I will switch on the time plot, the active current for the given surface. I will change the integration contour direction, so the integration current will have the positive sign. This is the active current. In nominal, at normal voltage, it's almost zero, but when the lightning pulse arrives, the current rises drastically. These are all problems for today. We simulated DC conduction problem to calculate the resistance, to find the resistance in case of ideal and non-ideal contact, and to simulate the ground connector. Also, we calculated the heating effects caused by the current flowing in the conductor. And we also simulated the AC conduction, the AC current flowing, and the transient current flowing.